All right, guys. So let's finish with limits. There is one more thing to share with you, and that is my nightmares. So do you remember Zeno, guys? And Zeno stated that motion is impossible. Why? Because to get from one point to the next, you have to cover half the distance. And to cover half the distance, you have to cover 1/4. And to cover 1/4, you have to cover 1/8. And to do that, you have to cover 1/16 of a distance. And of course, many of you, you're walking around and you don't bother with this problem, since it seems that, at least so it appears, that you can open the door and you can leave the room. Now, is that paradox of any meaning? We did this Orn experiment, correct? I did finish it with you. And we noticed that that's actually a very interesting paradox. Some people in probability had this. I reviewed some ideas from calculus, and they were troubled. They were troubled. One person, I mean, was particularly troubled. He thought that that the solution that was presented kind of, well, it's sneaky. So that Orn experiment was supposed to show you that, well, you have two possibilities. One possibility is after infinitely many steps, you get infinity, or the other possibility, after infinitely many steps, you get zero. I hope you remember that paradox or thought about it a little bit. Right? And yet another possibility, Nicole asked, well, maybe time never reaches 12, right? Maybe if you were to do that, time will somehow respond. And that's also something to pursue in physics. I mentioned relativity theory, very strange theory that tells you that that you see that basically you cannot compare one time to another exactly, right? They're just everything is changing when you move. If you move very, very rapidly, time slows. Compared to it slows, I mean, you'll feel the time is the same, but compared to what happens on the outside, for you, time is running much slower. But now here is my experiment, my nightmare, guys. So I am just an insect walking in a one-dimensional segment here. You can imagine this to be a video, my universe being a video that you're watching, indifferently perhaps. And imagine that in this video, you are seeing this new screen. And in that screen, it takes 1 second to move from point A to point B, right? You know that on the screen, you can make the video larger or shorter, right? Now, if I make that screen larger, guys, if I make it this long, stretch the screen, you know, I have a big screen, I can stretch that video, correct? If I stretch that screen, how long will the insect travel from point A to point B, please? Let me know. Well, how long? I mean, the video, how long does it run? If you have this screen and you're watching a movie, and now if you have a bigger screen, or if you stretch it onto a bigger screen, does the runtime of the movie change? That's what I'm asking. In other words, if the initial movie is 1 second, no, right? You watched movies on your small phone and on a big movie screen, and the movie remains the same. But you can think of the big screen or the small screen as showing exactly, well, they're showing the same space. From the outside, the space looks longer or shorter, but intrinsically to the space, it did not change length, correct? You understand what I mean? So imagine you have a very, very big screen, and on that big screen, you are stretching the image. The movie runs the same amount, it appears. You agree? Now let's adjust the scale a little bit more cleverly. Are you ready, guys? let's be more clever about adjusting this, the scale. Now, I'm going to create a snowflake. It's a von Koch curve. It's a very simple curve. And here is what I do, guys. I will stretch the screen in such a way that, look at it, the essence is that this line used to be of length 1/3. I divided this into thirds. I remove this middle line and I make this 2 copies of 1/3. You see, I can either stretch it or I can remove the middle section and replace it by 2 sections of 1/3 each. Do you agree that the screen is now longer? It's still one-dimensional shape, but I just kind of folded the screen. Imagine I have this up and I folded the screen like this. You with me? And now the screen looks longer. Do you agree? It's now, how long is it? It's now 4/3. You agree? It used to be 3/3. 1/3, 1/3, and 1/3, and the middle 1/3 was replaced by 2 copies of 1/3. So now it's 4/3. You're with me? How long does it take the insect to travel from point A to point B? Why longer? If you say, you guys, you're so familiar with stretching the movie this way, but why can't I not distort it like this? If the movie is like this, why can't I make 2-dimensional distortions to it? Yes? What's so special about this distortion? Imagine this is a flexible screen that you can fold, or imagine making the screen digital. Why not? Right? Run like this. That's where the movie is shown. Yeah. So next, guys, I will divide each of the remaining sections into thirds and replace the middle thirds by 2 copies. So 1/3 divided into 3 means that each segment is now 1/9 length. Do you agree? 1/9 of a length. And so what happens? This used to be 1/3. Now it's 4/9, which is more than 3/9. This used to be 1/3 and now it's 4/9. This used to be 1/3 and now it's 4/9. How long is that new screen? Could you tell me, please, in terms of the original? How long is it now? 1 second is the video, but how long is the screen? You see, first screen used to be of 1 length of itself. Next screen is 4/3. Do you agree? You all see that it's 4/3? And now 4/3 squared. You follow why? Because what I do in terms of length, I multiply the length, I scale it by 4/3. Do you see that? That's what I do. Because each segment, look at it, I'm using distributive law. At least that's how I think of it. Distributive law, guys. I say this segment, 1/3, I make it 4/9. What do? I multiply by 4/3. The next segment by 4/3, the next segment by 4/3. Do you understand how I reason this to be 4/3 squared? So I made it longer, bigger, whatnot, right? You see what I mean, guys? Just to be sure. What do I do with this length? I change it by 4/3. What do I do with this length? 4/3. What do I do with this thing? 4/3. 4/3. I multiplied it by, right? So it's 4/3 multiplied by this length. By what? What's the length here? It's 4/3. So it's now 4/3 squared. I hope you can see it, guys. You have to, you see, it's the distributive law, nothing more. Like this segment times 4/3 plus this segment times 4/3 plus this segment, right? So it's really 4/3 multiplied by each segment. I factor the 4/3, I add the segments, and I see it's 4/3 times the previous length. I hope you can see that, guys. Yes? Right? Now, you understand what I do next, guys. And next, I continue doing it even into more segments, you see? I do it even into more segments. So now what do you think? So in other words, I replace each 9 segment, and each 9 segment I replace by, instead of having 3 copies of 1/27, I now have 4 copies of 1/27. So the full effect is now the length of that next screen is what in terms of the original? The original was 1. The third screen is what length? 4/3 cubed. Guys, one person sees it. What about the rest? 4/3 cubed. How long does it take the insect to travel along that path? Let me know. At least from my observation. 1 second. If it travels at all, right? 1 second. You clear? Now let me show you that screen. This is this curve generated. Here it is, guys. Oh yes, here it is. Can you see it? Here is the line. Here is the next step, the next step, the next step, and you continue ad infinitum to produce the actual path. You continue deforming it, 4/3, 4/3, 4/3. Right? Now, why is it such a scary nightmare, at least to me? So I hope you understand, guys. Very basic arithmetic, and still it, distributive law, and still it shows us something. What do you think is the distance for the bug from this point to that point? From the initial point to the last point? Can you guess what's the distance between those 2 points now? Because the bug is attached to that curve. You understand? The bug cannot go through two-dimensional space and make a shortcut. The bug has to move along this pathway. How long is the pathway that the bug travels through? In meters. Let's say if it's measured in meters, how long is that pathway in meters? Infinite meters. Okay, infinite meters. It takes infinity to get from point A to point B, distance of infinity. Do you understand? And if you ask, what about from this point to that point? How long do you think that is? From this point to that point, how long do you think is the distance? Same. Infinity. Actual infinity, not even approaching infinity, actual infinity. And it's not infinity by Elazar, you have to be careful, not infinity by 2, because you have to reason why is that the case. Look at it, each scale, no matter what distance you take, it was amplified by 4/3, 4/3, 4/3, and that number is bigger and bigger and bigger. And what do you think is the distance between any macroscopic point here and here? Just take any point on the curve, any 2 points you can select, no matter how close they appear on the screen. Do you think what's the distance between them? It is infinity. I hope you guys, you're not just saying that, but you try to comprehend what it means, right? I right away want to quote, what was it, Бандитский Петербург. Мне до него последний шаг, но этот шаг длиннее жизни, which means to get to that great city of my dreams, I have to make but one step, but that one step is longer than life itself. Yes? And that is pretty much my existence. You see, you will graduate or fail, but what would happen to me? A Groundhog Day. New people will come and stare at me with indifferent eyes. And after those, new indifferent eyes, and then I do not make even a single step forward. I am stuck in perpetual paralysis. As they say in Hebrew, among sinful, ben levavot adishim vechotim, among sinful and indifferent hearts. And that's what I dream about. Good? That's my nightmare all the time. So, I hope you understood what it means, guys. So it's very, very, here is Zeno's paradox, right? But you see, this idea of length is such a strange idea. What is length? Something could be, it appears short from the outside, extremely long when viewed on the inside. The distance of this curve between any points on the curve is infinitely far. Good? And that's the simplest curve. It happens all the time. That's the simplest curve that I can show you for which that's true. And now, guys, let's abandon limits and go into the main problem of calculus, which is first main problem of calculus. It is the tangent line problem. You see, guys, we're now on the second section on derivatives. And by the time we reach trigonometry, you have your first exam. So we have some time to go. Okay, and here is this question. The idea of the derivative. So given a curve C, how do we find the line tangent to that curve at some point AB? Okay, in other words, how do we find a tangent problem? Now, before you even answer it, guys, I'm sure if you kind of still can tolerate, you ask you why on earth would anybody be bothered with such a problem? And let me ask it first of you. Why would anybody care for the tangent to the curve? As they say in real life, which by the way, it's always confusing me. What's real? What's not real life? But why would anybody care about the tangent problem? For other sciences, perhaps, right? But like chemistry, like what? But right? What's close to Earth? You're young people, right? You go to bars, I presume, and I pretty much, I can tell you a pickup line, right? You go to a bar, and you can say to a pretty girl, "Baby, let me be your derivative, so I may lay tangents to your curves." Okay, and of course, if she knows that, well, you studied calculus, she knows that you are a man that knows what he's doing. Good. So do you know what you're doing? Let me give you an illustration of what's calculus about. Okay. Again, I mentioned that Nicole was asking, what's the big picture? Always look for the big picture. Okay. So when we study curves, okay, right now we're not yet sure that we want to study curves, but suppose that that's our goal. Okay. We want to study curves. Now, a curve can be very complicated, but there is an instance of a curve that's very simple. What's the simplest type of curve? Can anybody tell me? Let me give you a hint. What's the simplest type of curve? A line. Now, why is that a hint? Look at it. You see that I'm holding something here and I'm holding something here. You don't see what is in between, but your mind connects those points. You imagine a stretched, invisible string. That means that a line is determined by precisely 2 points. You understand? The fact that you can see that mathematically means tell me 2 points and you know a line. Okay. Now, by that analogy, you think the next complicated curve, how many points do you think it needs to be determined? 3, precisely. You need 3 points to determine the next complexity. Okay, so the simplest would be 1 point, the next will be 2 points. Any degree 2 polynomial is determined, its graph is determined by specifying 3 points. Okay, any quadratic is decided by 2 points. The next is cubic, decided by 4 points, and so on and so forth. You understand? So the simplest instance of a curve is a line. And so the idea of calculus is to use the simplest instance of a phenomena to describe the more complicated phenomena and do it very simply. So for example, when you play video games, you have, let's say, you have a fabric or you have a person moving around, but what is that person? It's a simplicial complex. It's just a collection of mesh of triangles. And it's very easy to understand how to rotate and move triangles using linear algebra or using something else, right? So all you have to do is just apply that very simple calculation millions of times, and you have a very good simulation. Do you understand? So when you think calculus, what is it about? It's basically playing Lego. That's what it is about, okay? Build up complex phenomena out of very simple blocks. So when you study curves, look at it, guys. Here is a curve. I can imagine it's a link of many line segments. It's a chain of line segments. If they are small enough, that will look or resemble a curve. Do you understand? And why would you want to study link of line segments? So, I mean, if I had the funding, I would have built your roller coaster, right? And then you would have to calculate whether you survive on it or not. Okay, and you can do that simply by understanding if you would survive by riding a roller coaster along a small line segment. You understand? So that's my work or energy, whatnot, explanation when I talk about dot product in Calc 3. So to make it, yeah, so you understand, guys. So to just to take a small sidetrack for a moment and to speak about calculus. So what do when you study? When you want to study, think about the image that you're seeing on TV. It's built of pixels. If you want to study sound or any other wave, the simplest wave might be the sine wave, right? So can you build up a bunch of sine waves on top of each other and create a complicated wave? Okay, and that's Fourier analysis. You build up waves out of very small instances of waves by adding them up. Good. Then when you study areas and volumes, the simplest thing for which you can calculate area is a rectangle. So you can imagine that you have lots of very thin rectangles, pencil thin, even thinner, microscopic, hair thin rectangles, many of them, and you just add up their areas and you get the area under the curve. You understand? So the idea is to find a simple instance and to describe that phenomena that you're studying with the simplest instance of that very phenomena. Good. Now, another thing, of course, if you study physics, the tangent line problem is that if you are moving along a curve, and if that curve is not line, that means there is a net force. You see, even if you're moving with constant speed, but you're moving in a circle, you would feel some sort of pressure that throws you against the wall. You understand? So there is a net force that is acting on you. Now, if you turn off the forces, in this case, let's say the rocket is in space and you turn off the engine, the rocket will depart from the curve along a line that looks like it's just touching the curve. You understand? It will depart that curve, which, by the way, is this thing that we're studying. It's called the derivative, but I don't like that word. The German word for what we're doing for derivatives is Ableitung, which means lead off. You understand? If something departs and is led off, and that's very physical here. As you see, it's like this rocket is led off the curve. So the tangent line is a sort of lead off. That's why we study it in physics. It's very important there. So it meets at one point, Christian, essentially. At least locally, it looks like it touches this, this line and this curve. They touch exactly at one point. Good? That's Newton's observation there, right? Good? In some sense, if you think like a Lego block, you can think of it as almost natural. You understand? Because you think of when you're traveling on a curve, you're thinking like you're traveling on tiny, tiny line segments. Each time you change a motion or move somewhere, you travel along a tiny line segment. So the intuition feels like, well, when you apply force, it's like you are altering the orientation of that line segment. And then when you stop doing it, it's the line segment is staying the same. You understand? Almost, it feels sometimes almost natural. Of course, when you hear it, right? Do you understand what I'm saying, guys? You think this is what my advice is for how you study. Don't memorize. I know you will not listen, but believe me, right? Don't memorize, visualize what you're doing and try to understand what is the lowly origin of that idea. If somebody is fanciful and looks like he is new rich, right? Well, drives bling bling cars, whatnot, right? Golden rims on the car, whatnot. You think, okay, this person is masking the fact that the person is poor and is insecure. So you understand something by looking into its lowly origins. You understand a person by looking at his lowly beginnings. And so you do with mathematics. Good? And we shall see, guys, here's another thing. You might, of course, ask, what is this for? What is the point of it? But again, very often when you ask this question, I think this. This means that you have a very short and very narrow point of view. And the thing is that many very interesting things, they end up being mathematically equivalent, or there is a huge chain of mathematical thinking that leads to ideas that physically or emotionally don't feel the same. They don't feel the same at all. You don't even associate between them, okay? And so you see one person actually that's here, to my surprise, has not seen Indiana Jones. But I'm sure it's only one person. Of course, guys, all of you have seen Indiana Jones. Am I right? Like, I will not find a person here, maybe one, but that has not watched Indiana Jones. My God, millennials or whatever you are. So do you remember the Holy Grail episode, right? So this guy goes and sees many shiny, beautiful golden diamonds, whatnot, grails, right? But that Holy Grail is the simplest of them all. It's very unsightly. And the same thing you should think about anything. Is the most interesting things are the things that are underneath your nose and you just do not notice them. You just do not realize the long and complicated chain that links them to that thing that you are truly seeking. Good? And here is just at a glance, guys. I will try to show you, again, you might not be convinced that this is an incredibly important result. Maybe you're not convinced of that right away, but my point is, you think tangent to the curve, and here is an application that seems nothing to do with tangents to the curves, okay? And let me show you that application, if I may, okay? So in the 18th century, a mathematician by the name of Buffon, I think, right? Buffon figured out how to calculate pi by taking a bunch of needles and throwing them on a rolled piece of paper. Let me show you what he did, if I may. Here, guys, look what happens here. So the space between the lines is 2 needles long. Now here is what you do. Just scatter the needles on the paper and count how many needles intersect the lines. How many needles lie at an intersection of a line? You see what he's doing? So 101 out of 314. And the ratio that you obtain is 3.10, roughly speaking. It just needs to throw more needles. That would work when you throw more and more needles. If you throw infinitely many of them, you'll get pi precisely. Okay? Now, if you want to understand why such a thing would work, for that, naturally, you need to think mathematically, right? And how does it relate to the derivative? Here is my calculation to explain why that happened. By the way, I present that calculation at the end of probability theory when I teach it. The requirement to understand it with my presentation would probably be, maybe I can explain it eventually, but definitely you need all of Calc 1, better Calc 3, because it involves change of coordinates, double integrals, whatnot. Here I calculated that the ratio will be 2 over pi. And if you think this way, it also it will be natural. You understand? I mean, if you learn to think like I'm trying to suggest that you should think, such ideas become natural. You understand why that works. You come up with it. And what does it have to do with tangent lines to the curve? Well, it's a long distance. You see, guys, this operation that I do there with double integrals, it's antiderivative. What is a derivative? Derivative is related to finding tangents to the curve. Okay, so it's a lot of ideas from calculus, beginning from tangent line to the curve, anti-tangent to the curve, how that relates to area problem, all sorts of things like that, to understand why that phenomena happens. Okay, and that's just still a phenomena very, very close to, it's mathematics still, right? So some other things that are that seem farther might take a longer chain of reasoning to get there. So I hope, therefore, you are excited. By the way, now let's go and talk about the tangent problem. I hope I convinced you at least a little bit. Maybe some of you I haven't convinced at all, or you haven't listened, but I convinced you a little bit that it is something worth knowing. So it's very easy, guys, to understand what is tangent to a circle, correct? Because tangent to a circle means what? It means that the line intersects the circle exactly once. A line can intersect, you can just think of it geometrically, either not intersect the circle or intersect in 2 points, in which case it's a secant line, or intersect in 1 point, in which case it's a tangent line. But that definition will not do in general for arbitrary curves. You can see that this red line that I drew here is clearly not a tangent line. It does cross the graph only at 1 point, but it kind of pierces through the curve. We don't like that. I imagine a bullet passing by maybe a hill and just grazing it rather than going through it. You understand? So tangent means a gentle touch like this. It doesn't mean to go through. And so we are trying to capture that idea. And before we can talk about that idea, guys, we need to talk about a slope of the line. And because I'm convinced you know it, I'm going to ask, before I explain, what is slope? Give me also, I want 2 things, guys. Not just the dogmatic explanation, it's whatever it is, how to calculate it, but what is the idea? What are we trying to capture when we talk about a slope? What concept are we trying to identify or communicate? Well, rate of change is too general. Rise over run is calculation, but why? What rise over run? What are we trying to talk about? Relation of x to y, a little better. The sharpness of an angle, that's much better. But specifically, sharpness of an angle is another way of saying what? How steep a line is, right? How steep is something? You agree? So how steep is something? Well, you can break, imagine walking at an incline. Maybe the incline is flat, maybe it's like this, right? When you walk at an incline, you can break the motion into horizontal motion and vertical motion. That's easier to analyze, right? So you can imagine if you move from one point to another, that there was some amount of horizontal displacement and some amount of vertical displacement that has been undertaken. So for instance, here, imagine you walk, you begin walking from this point and you end up climbing to that point, okay? Now, you can see that the horizontal displacement is this segment and the vertical displacement is the vertical segment. You agree? I just broke how much you changed position horizontally and how much you changed position vertically. Now, if the line is very steep, there would be, for very little horizontal change, there would be huge vertical change. On the other hand, if the line is essentially plane, you can walk very, very big distance horizontally and essentially not change elevation. Do you agree? Guys, you understand what we're communicating? Steepness, you can understand that you walk along this line, you just measure the relationship between horizontal distance traveled to vertical distance traveled. Good? Now, if you are walking along a line, look what happens, guys. You see? Because the angles of any horizontal line intersecting this one line that I drew is the same. You see, I have the blue horizontal line or the red horizontal line, they make the same angle. And similarly, for any vertical line, they make the same angle. You can see that I draw here a right triangle. And those right triangles are proportional. Between any 2 points on the line, the right triangles are proportional. Can you see that? Now, what is proportionality? Proportionality means double one side, double the, let's call it the run, the horizontal displacement. Double the run, you will double the rise. Triple the run, you will triple the rise. Half the run, you will half the rise. And the same thing if you multiply the height, the rise by some constant, the same constant will multiply the run. Do you agree? Some of you look frozen. You see, guys, it's just this. Think about proportionality, right? What do I know about proportionality? Increase one feature, you must increase by the same factor every other feature. Yes? And so how do we measure that very simply? Because, you know, if it means that one quantity is multiplied by, let's say, 5, the other by 5, you can communicate that very simply without mentioning by how much it's multiplied by taking the ratio of those quantities. Because it's like, let's say, run multiplied by 5 divided by rise multiplied by 5, the 5s cross out. And you are trying to find that constant. You understand? What is preserved? In proportion, what's preserved, if my finger is as long as my nose, I doubled my finger. I doubled my nose, I preserve proportion, which means that the ratio is still 1. There is a 1 there, right? That communicates that they stayed within the same proportion. You understand? It's just a matter of communicating the constant. What remained? Good? So basically, in terms, the slope is just that measurement. For any fixed line, the blue triangle and the red triangle are the same. So that means that if I measure rise over run over the red triangle, and if I measure it over the blue triangle, I will get the same constant. You understand? Because those right triangles are proportional. I hope you see that. Right? They have the same angles, then that means they are proportional. Good? And so that gives me a very easy way of calculating, of figuring out whether a point is on a given line. That gives me, now I can write an equation of a line. You see? So I know that a point, look at it, I'm gonna draw one point, okay? So what makes, let's say I'll put it in orange, right? So what makes this point, let's call it XY, and I will call this point for convenience just AB. Okay, what makes the point XY on the line? Well, look at it. If I use XY, if I walk towards XY, I have this orange triangle. So I have that Y minus B divided by X minus A. I just measure how much I displaced horizontally and how much I displaced vertically. The ratio is going to be the same slope M, the same slope as if I calculate it from any other 2 points. So if I know that slope, the ratio will stay the same. You understand? If on the other hand, let's say I selected a point lower, if I selected that point here, let me just make a comprehension check. So this is XY, and let's say this point is AB. Now tell me please, what's the relationship with, and the line has slope M. Maybe I should say it in black. So the line has slope M. Now I have a very simple question to ask. I selected, you see where the point is, XY, it's over here. Tell me please, what's the relationship between Y minus B divided by X minus A and M? Are they the same? Or is one of them larger? And if so, which of those quantities is larger if they're not the same? You see, I drew the point XY somewhere in here. Okay, so what do you think in this case? What's the relationship between the left quantity and the quantity M? M is larger in this particular drawing. You understand? Do you all see that, guys, that M is larger? I hope so, guys. You see, that's another thing. You see, you're in calculus. Well, I put this point over here, below the line. If I put it below the line, it means that, look at it, what would happen? If I put it below the line, I'll draw it in the green, right? Look what happens. If I walk if I walk to this point, here is how much I climb for that same horizontal rise. For this horizontal, that's how much I climb. Now, to be actually on the line, I would have had to climb a bit more. That means that rise over run for the actual line is bigger than this quantity. So that means that Y minus B over X minus A is smaller than M. I hope you understand that. And it's not from the picture, you understand? I can use the equation, I can be completely blind and not see the line, and I can tell whether a point is below a line or above it, easily. And when the slope is equal, that means the point is exactly on the line. You see what happens, guys? Here is a point, and if you tell me what's my steepness, you communicate the slope. You tell me, you tell me then how this point is related to the other point. Let me check if you understand it. Okay, guys. So we have the point 1, 3, and slope 5. Okay, so we have a line that contains this point, and the line has slope 5. Now, what does it mean to have slope 5, guys? It means that if you walk on this line, if you decide to walk 1 unit, the equivalent of 1 unit horizontally, you necessarily must have climbed up 5 units. Do you understand? So that's how this communicates steepness. If you moved horizontally half a unit, you climb 5/2 units. Understood? Very easy. So I want you to tell me, is the point 2, 4 on the line? If not, is it above or below the line? So go ahead and tell me. See, without seeing the line, I want you to understand that you have to use your inner eyes, your logic, your mathematical sonar. And that's what? Come on, it should take you 2 seconds to figure it out. Okay, somebody says below. So tell me, point below line, equal on the line, or above the line? Okay, some people say below. So very simple, we can calculate, right? So slope is supposed to be 5. So what I do is I take this point to 4, and I see if I were to travel from 1, 3 to the point 2, 4, right? I would have traveled 4 minus 3 divided by 2 minus 1. And so I would have traveled exactly what? The slope in this case is 1, correct? Slope is 1, which is less than 5, which means traveling to that point, I only climbed 1 unit. I moved horizontally, I displaced 1 unit, and vertically I moved 1 unit. But I should have moved vertically 5 units. Is it clear? To be above. So it means, so it's very simple, correct, guys? You don't need to see a graph or whatnot or a picture. Besides, if somebody provides this picture, how do you get it? Good. And so now I know how to find the equation of a line. So without even seeing it, any point xy, remember, point in our case has 2 coordinates, has the x coordinate and the y coordinate. A point xy is on the line that goes through the point AB and has slope m. If calculating the slope using the points xy and AB, this is calculating that slope, will produce the slope m naturally, right? Because that means if I were to travel from point AB to the point xy, I would have had the ratio of rise over run will be that that corresponds to the line naturally if I'm on it, correct? Easy enough, good. Now we are finally hopefully able to define what is the derivative, or we're going to call it derivative later, but we're going to try to explain what is the tangent line and what is the slope of it. So here we can use limits. You see, I want to calculate the slope of the tangent line at the point P. For that purpose, I can say, okay, let me take another point. Let me create a secant line. Take the point Q. And because the point Q will actually be moved closer to P, I will just give it coordinates X and the other, it's on the graph y equals f of x, so the other coordinate is f of x. So this point is x f of x. Good. And you can see that when the points are distant from each other, I can clearly see that this is a secant line. But as I move the point Q closer and closer to P, do you see that? The distance between those 2 points decreases. Yes? And I can see that if those 2 points become 1 point, then that will be a tangent line. Let me show you an animation just to reinforce that idea. Ready? Here is some graph, I think Grant's favorite. Here, let's say I would like to know the slope of the tangent line at 0 here. Good. So what can I do? Look at it. So here is the other point. You can see that I created 2 points here. Yes. Now, what I do is I move that second point closer and closer to the point at which I want to create the tangent line. Do you see what happens? Because those 2 points are merging into 1 point, the graph is more and more just touching the curve rather than intersecting it. Clear? And so you see, eventually, if I move that point very close, look how close it is. Eventually, when I move it really, really close, it will look to you like it's a line going through just 1 point on the graph rather than through 2 points. And that's exactly is the idea. So when you say its, Moshe, I'm not sure what you mean by its. So 1 point is movable, the other one is fixed. So I take the movable point and move it closer to the fixed point so that I will be able to calculate the slope of the line that touches only through 1 point. Because you see, if I just fix 1 point, I cannot calculate the slope. I need 2 points. So I just make the other point merge. And that's how I take limit. Good? Do you understand what's happening, guys? Yes, let's see if you do. Because now let's first of all understand the definition here, guys. Here is the slope of the secant. This is the secant slope. You understand that in general, if the graph is y equals f of x, what does this mean? It means give me a first number, and the second number is calculated from the first, right? I'll go give you an example in a moment to be sure we understand it. And so f of x minus f of a is just what? It's just from this point. This is x f of x, and this is a f of a. F of x minus f of a is my rise, divided by x minus a, that's my run. And what do I do to make the points go closer together? I want to make x approach a. Do you agree? I want to make the x coordinate approach a, and we get this definition: limit as x goes to a of f of x minus f of a over x minus a is the tangent slope. Everybody understands, guys? You understand how this definition was built, right? It's so natural. You don't memorize it. You just understand that there could not be anything else. It's very obvious. And so let's see if you understand it. Before I explain anything.
Professor, so x in this case would be the second dot approaching a?
Yes,
and that would be
x f of x. The dot has 2 coordinates. X is the x coordinate of that dot. So let me just show again the drawing, the diagram. Here is what you specify. Look at it, guys. So you see this? Where do you see x? So it's this. Let's say, let me move it a bit further. Oh, it's a bit steep of this. Let's see. What should I change this?
So as you go further away.
1 second. Let me just put here x squared. X squared. That might be a nicer curve. Okay, just to make it easier for you to see what happens here, right? So you see here, where do you see the x? The x is here. This is my x. You see, that's my x. Now, when I slide this point closer, I can control that by doing what? I can control moving that point closer. But you see what's happening. Just pay attention to the x coordinate. It's getting here. In this case, x is approaching 0. And what do you see? Look at it. The line appears to be getting more and more. Well, it doesn't kind of go further, but it will get horizontal. Good?
Yeah, thank you.
Okay. Now help me with this calculation, please. I want you to find, I said the equation, but actually an equation. There are many equations. Find me a tangent line for the graph y equals x squared at x equal to 2. We'll do it together, but let's see if you can set it up and find it before I do it. Sure, Grant. So what do you do, guys? If you don't remember all of it, just remember what is the idea. We have a curve. You right away think, well, I don't see the curve. You don't need to see it. I have a curve. I have a formula for it. I know what it means to be on the curve by the formula. What do you need? You need a line. So therefore, select 2 points on the curve. What's the point of interest? The point of interest is where x is 2. Good. And calculate the slope of the tangent line. Once you have that, everything else is simple. And also, of course, if you are not in a situation where it's extremely inconvenient, of course, turn your camera on so that I can look at you and not be bored. Thank you, Erin. All right, this is first. I will solve one for you and you will solve the next for me. Good? So very simple, guys. You see, you don't need to know too much. Look at it. When I say x equal to 2, that means what's my coordinate? What's my actual point? When I say y equals to x squared, that means that many of you are confused by that x and y. That just means I have 2 coordinates. The second coordinate is the square of the first coordinate. Do you understand? So even if I don't see the curve, I know, for example, that the point 1, 1 is on the curve. Why? Because 1 on the y equals 1 squared. 2 and 4 is there. 5 and 25 are there. Good? You might have plotted this curve. Actually, I have the curve available. We're going to see it online afterwards, right? But you don't need to be bothered, right? So what is this? Look at it, guys. So the point is 2, 4. Yes? And I want to calculate slope at the point 2, 4. So what do? I pick another point. This is my point P. That's the point at which I am interested to calculate. Now I pick the point Q, and the point Q is going to have arbitrary coordinates x squared. The point has to be on the graph. So it's x squared. You understand that, guys? Everybody is with me? Right? And so what now? And now I calculate the slope. So the secant slope is rise, which is x squared minus 4. That's the difference of the y coordinates, over run, which is x minus 2. That's my slope. Good? Now, this is the x must be close to 2. Do you agree? I would like to make x equal to 2, but if I do so, I will have 0 over 0. I cannot do that, right? So I'm going to make the other point go towards 2. You understand, guys, how that works, correct? It's all intuitive, I think. So you take limit x going to 2. You understand what I write? It's like my hand is moving itself because it knows where it wants to go. You have that feeling? So now I can do what I learned before. I can factor out x squared minus 4 into what? So that's limit as x goes to 2. That's x minus 2. In fact, I will erase it because I have it written right below. Here. Good? And then when I push limit as x goes to 2, what do I get? I get that the slope is 4. Okay, is that going to be truly the case? Let's see in the picture. This is x squared, that's the graph here. I can zoom in. Now I am interested in a equal to 2, you see? So here is the point 2, 4, do you agree? This is the point 2, 4, and now let's see. So let's make this a bit more distant. Now let's zoom in. Okay, this is 2, 4, and then when I zoom in,
I have a question for the test. If we use the because we have graphing calculators, we just use graphing calculator, and then do we still have to show all the work, or can I just put in the answer?
Why would you use a graphing calculator?
Be able to put it in.
What for? Well, I mean, you have computers. Yeah, well, what exactly do you want to do? I'm sorry, I misunderstand.
Like for example, like you're writing out all this math. If we put in the graphing calculator, it would calculate it for us.
Ah, you mean why do you need to think when you have a calculator that does it? Don't worry about it, because on the exam, I will ask conceptual questions. Besides, the calculator does not. You are right in that sense. More and more machines are getting smarter, and eventually they're going to replace humans in their abilities in everything. So learning languages becomes less and less important, because you can just write something in Google Translate and it will just translate, and actually pretty accurate. In many cases, even you give it a poem and it translates it more accurately. So then you can make a case, why would I want to learn to speak? Because
no, I'm just saying for the test, we have to show out, like break down all the work.
Oh, for the test, it will be conceptual questions. You understand? I will try. I mean, you see, you have very smart. You're correct. You have very smart programs which, without putting a lot of my own effort, makes it hard for me to police whether it's your answer or not, right? Internet or whatnot. So people become stupid, but machines become smart. But I want people to still remain somewhat on par. You see, people still need to think. So my questions on the exam and on the final especially are conceptual questions, you understand? So you would not be able to put it in the machine and get an answer without a person involved. The way I ask the questions, it will not be possible. Good. So what you should know, guys, is understand the material and not just blank plug something in, or, you know, if you see plugging in, machines do that very well. What you try to do is have a sort of view, understanding of what it is, right? Now, the case that what remains important, it's of course, I can tell you that at the end of the day, human reasoning, most likely, that's my impression, is going to become obsolete, but not obsolete just yet. Intelligent people are necessary still. Not for long, but still. Right? And also it's a sort of, you know, something else might do it, but if you're religious, you can say, well, why think God already thought of everything? It's really a similar, if you see Elazar laughs, right? It's a type of similar thing. But the calculator can do it, can you do it? Right? I mean, why do push-ups if there is Arnold Schwarzenegger that can do 1 million of them, right? Why would I do even a single push-up? You see, guys? The question is, of course, yes, and no calculators are needed for this. That's exactly right. All right, let's get back to this thing. So what is the equation of the tangent line? You can definitely take a calculator and it will figure out what's the tangent line, but that's not an interesting problem. That's just a I'm just showing you how to calculate it. That's not at all what we're up to. But if I told you calculate probability by throwing needles, I think you would need a little bit more thinking. So y minus, so basically we have the two coordinates. We have the slope and we have the coordinates 2 and 4. Yes, 2 and 4. And so when you calculate it, you see that y minus 4 over x minus 2 is equal to 4. So that means that y minus 4 equal to 4 times x minus 2. All right, guys, and now let's see if you can do the next question. Here is minus 3x squared plus x plus 5. And calculate, please, what is the slope of the tangent line at x equal to 1, if you can. And in general, can you do it at an arbitrary point a, f of a? By definition, since Abhishek whatnot, I mean, this is just just the very, very introduction, right? You can do it any way you like, of course, but yeah. I want to see if you understand the definition and you can apply it. Well, Abhishek, f of a plus that thing, yes. Alrighty, let's do it together. Good, together, guys. Let me do it for 1, but I will actually show you that I would have not calculated it at 1 because it's a waste of my energy. I can solve for all derivatives right away. And maybe by that see the pattern, okay? So Yes. So let's see what happens here, guys. Okay, so what I have is, here is my function, and I will try to calculate the difference between the vertical, which is f of x minus f of 1, divided by x minus 1. You see, x f of x is my sliding point q. 1 f of 1 is my fixed point at which I calculate the derivative, correct? So then I take the limit as x goes to 1. We have in the numerator, we have this is f of x minus f of 1 divided by x minus 1. Simplifying it, you get minus 3x squared plus x plus 2. I'm not going to bother explaining how to factor it. If you know, wonderful. If not, I will do it another way. So then you can see that you can factor it into minus 3x minus 2 times x minus 1. The x minus 1 crosses away. I push x towards 1. And what do I get? I get minus 3 minus 2, which is minus 5, as some of you have correctly solved. Good? The slope is minus 5, which means if I move horizontally 1 unit, I descend 5 units down. Good? Now, of course, maybe some of you right away think, well, how did I factor it? You don't remember how to factor, or who knows what else. But let me show you how I would actually calculate it. And how did I even know how to factor it? You see? That's my equation of the line. So it's y minus 3. That's y minus the displacement on the y-axis divided by x minus 1 is minus 5. So you have this line. So here is the general situation, guys. Suppose I wanted to calculate it at the slope at a, f of a. You see what I do? I write the function f of x, and I write subtraction of the function at a divided by x minus a. Then group things that look alike together. You understand? Group things that look alike together, which means minus 3x and minus 3a, x and a, 5 and 5. You can see that minus 3x squared minus 3a squared, I can factor out a minus 3 and I get minus 3x squared minus a squared. X minus a is here, 5 minus 5 is gone. Are you with me now? Guys, you understand? Good. And then from here, x squared minus a squared, it's x plus a, x minus a. Factor out x minus a, this is what you get, look at it. Minus 3 times x plus a. I just remove, you see, I take this factor out, this factor out. So it's, you can see x minus a times 1 is this part, x minus a times this part will be minus 3x plus a, x minus a. So what I have is an ability to cross away x minus a, and I push limit as x goes to a. And what do I get? Look at it now. You see this. This is what in the square parentheses in the brackets is what remains. Now when x becomes close to a, it's minus 3 multiplied by a plus a, or minus 3 times 2a plus 1. And what is that? That's minus 6a plus 1. Now what's the advantage of this? Look at it, guys. Now this tells me right away how to calculate all slopes. So if I wanted the slope at 1, I replace a equal to 1. Do you agree? Let's say I want now to know what's the slope at 1. So I just say minus 6 plus 1 and I get minus 5. You see how nice? Now, what you see is that it's the x coordinate that's multiplied by minus 6 and you add 1 to it, and that will be the slope. You understand? Just take the x coordinate multiplied by minus 6 and add 1. So now this formula tells you immediately how to find the slope for any point that you might be interested in. So you did not spend that. I don't think it's harder. And I think it's actually easier than to solve it at a specific number. And right away you get the slope for all possible places where you might want the tangent. You understand? You see, instead of focusing on touching at one point, you can now touch the curve everywhere you like. Good? You understand, guys? Conserve your energy this way. So, in the equation, of course, it's y minus the y coordinate times the slope, x minus the x coordinate of the slope. Now your turn again. You can do it in the general setting, or you can do it for a particular point, up to you. Tell me, what is the tangent, the equation of the tangent line, and very specifically, what's the slope of that line? If my function is root of x and I want to do it at x equal to 9. And see if you can do it fast, guys. So by the end, before the first exam, this question you should solve in under a minute. That's right, Abhishek. We will learn a lot of shortcuts, but actually some of them, again, when is the first exam? Perennial question. Do you understand the material for the first exam? That's what you should ask yourself. You will be notified 2 weeks ahead of time. It's by the time we reach trigonometry. When I hear those questions, I think that's a good idea. Maybe I should just teach calculators. Well, it's up to you. You can make it an A or a 9, right? Does it matter? It's a 9 in this case, but make it an A if you prefer. I would have. Well, good, Aaron, good. Thank you, Abhishek. Thank you, John. Sure, you can write it this way. Guys, by the way, many of you solve y equal to, y4. Just what you should do is don't put any energy where it's not necessary. If you are asked find some equation, just find the simplest, fastest equation. If you are if you have to solve through the y-intercept equation or whatever it's called, then you can do that. Yes, Moshe, very good. All right, we had enough time, yes? Let's do it together. I'll give you more challenging questions, guys. Good, Cillian, wonderful. I'll give you more challenging questions after class if you want to practice with me, right? And if you want to play what, when, where, of course, I have a few interesting questions. I have one American question, see if you can answer that one, right? Yes. All right, guys, so here is how we go about it, okay? So at 9, you see we take root of x minus root of 9 over x minus 9. Do you understand why? Because x root of x is a point on the curve. 9 root 9 is another point on the curve. X has to go closer and closer to 9. Good? You understand, guys? You understand what the formula is, right? You see that's the important part here. The calculation is obvious. I mean, you can make, but the idea is what makes the formula important is what I would like you to see. So you see why x goes to 9, of course, right? That's we're trying to make the 2 points very close to each other. So now when you see a minus b, you like to multiply by conjugates. It's just something you love doing, apparently. So you multiply by root x plus 3 and divide. Division is completely to balance the equation. You never wanted to divide, you just wanted to multiply, but you have to not change the original expression. So what you have here is it's a minus b times a plus b. Square this minus the square of that, so it's x minus 9. And we have x minus 9 on the bottom, we can cancel it out. And we're left with 1 over root 9 plus 3. Do you agree? Now when x approaches 9, root of x approaches root of 9. And we see that our slope is 1/6. And so you can write an equation. There are many equations that identify the same line. You can write it in the slope form. It's a point xy is, you see what this equation is saying? It says that a point xy is on the line. If using that point to calculate slope against the coordinates 9, 3, I will get that slope is equal to 1/6. Good? So y minus 3 is 1/6, x minus 9. We are done. Now, what is the general pattern for this equation? If I wanted to find the slope at an arbitrary point a root a, what would be the slope? All you do is you take root x minus root a, divide by x minus a, and you take limit where x goes to a. You multiply by the conjugate, so you now get limit as x goes to a, x minus a divided by x minus a. And then here we have root x plus root a. Yeah? Because if you do it abstractly, you'll learn a bit more about what is this, what's the process about. Like 1/6, what's special about 1/6? What does it relate to the number 9? So then this crosses away. And what is your limit? Your limit is none other than 1/root a plus root a, or 1/2 root a. You see that? 1/2 root a. So that means that to calculate the slope, so this is what we did for 9, right? We take 1/2 root 9. That's how we got 1/6. So you just have to take the root of the number, multiply it by 2, and take the reciprocal. And you will have the slope for that particular function. Good? Beautiful. Moving on. Now, guys, here is that question with which we began the semester. A particle moves so that its position in time is x of t equal to 2t squared minus t plus 1. I want you to tell me what is the velocity when t is equal to 1, please. Can you do that? Do you remember how? Thank you, Abhishek. Be careful, guys. I see a lot of you are getting too interesting. And then you remind me why we calculated this way, okay? All right, so let's do it together. What do you say? Enough time, or you need more time to think about it? So here is that situation, guys. So velocity at 1 will be limit as t goes to 1 of x of t minus x of 1. That means x at some moment t minus the position at 1 divided by t minus 1 as t goes to 1. Now, before I calculate, could anybody tell me how did I arrive at this limit? You see, the limit looks like the slope, right? It looks like I'm trying to find the tangent slope. But conceptually, why do I do that conceptually? What was the conceptual idea that led us to this limit? Well, philosophy, right? The speeds feels very different from the geometry of the curve, even though the formulas are the same. Why am I taking the limit as t goes to 1? Why am I doing that? What is velocity? Velocity is change of position over change of time, but that only works if the velocity is constant. Do you agree? When you say it's same to the slope, right? You are comparing distance, proportional distance to time. So basically, you can graph if constant velocity, it's going to be a line. You agree? Constant velocity is a line because what you have is the horizontal coordinates is amount of time elapsed. The vertical coordinate is how much distance you traveled. You see that? So let's say if you're running at 6 miles per hour, it means in 1 hour you cover 6 miles. In half an hour, you cover 3 miles. Agreed? It's proportionality. What's proportionate? The number of miles covered by the time that it took you to cover it will be a fixed number. It will be the same number, which is 6. Clear? Because this amount of time carries this amount of displacement. That's how much distance you cover. But that only works with constant velocity. Now, things that move don't move with constant velocity. So what do? The idea here is this. You see what we do here? If we allow very little change in time, there will be very little change in velocity. With little time, there is little change. Right? The less the time changes, the less there was an opportunity to alter the velocity or anything else. Good? You understand that what's the philosophy? You see, guys, I mean, it has to be clear. I mean, it's not like, oh, how do I do it? There's a limit. This guy did this. But it has to be obvious. Right? When it's obvious, it's very simple. You all understand why I take limit as t goes to 1? Yes, I'm expressing something philosophical. I mean, if I never knew anything about speed, it would be very difficult for me to come up with this formula. I kind of have this experience. Allow less time, less change. Good? So that is basically saying that if t is very close to 1, then this quantity is a very good estimate of the actual velocity. Now, how do you calculate it? You take t going to 1, then you have 2t squared minus t plus 1. At 1, this is equal to 2. And so you have 2t squared minus t minus 1 over t minus 1. You need to know how to factor this polynomial, or of course you can do it better. I'll show you in a moment. We can do it better. We can find it at any moment of time, right? Then you can cross away t minus 1, push t towards 1, and what do you get? You get 3 times 1 plus 1, and that's obviously equal to 3. Yes? They are emotionally, or when you think about the philosophy, it seems that they're not exactly related, but mathematically, both are the slope of a tangent line. Mathematically, but not how you feel about it, right? Not through actual experience. So, what about the velocity at any given moment of time t? Well, I can make it limit as s goes to t, as one moment of time goes to another, of x of s minus x of t divided by s minus t. That in this case, I'm just trying to figure out the velocity at an arbitrary moment of time t. Do you agree? So not at 1, but I can do it simultaneously for all points, if I can do that. Now, what is that x of s minus x of t over s minus t? Well, let's see. This was my original function. Here it is. Here it is, right? So I'm going to write for x of s, it's going to be what? It's going to be 2s squared minus s plus 1, put it in parentheses, minus 2t squared minus t plus 1 divided by s minus t, and limit as s goes to t. Yes? Now here, guys, just group like with like. Look how fast I can do that. 2s squared and 2t squared. So that means this is limit as s goes to t of 2s squared minus t squared. Now minus Here I have s minus t, and 1 minus 1 is gone. You see what I'm doing? If you need, take a moment and see that you can carry that calculation. Do you see what I don't even need to think. I see this and I see that. I know I just need to factor this constant out. It will be s squared minus t squared. I see the constant here is minus 1. So I factor the minus 1 and it will be s minus t. So when I group like with like, it always has this pattern. It's very easy. If you want to, after class, we can train to do that pattern very fast. Good. So then all you have to do is just factor s squared minus t squared. What is that? That's just 2s plus t, s minus t, minus s minus t, divided by s minus t. And then you can factor out from here s minus t. And what are you left with once you factor it out? You now get the limit as s goes to t of 2s plus t minus 1, which becomes 2 times 2t, because s goes to t, minus 1. And so the result is 4t minus 1. So the result is that the velocity is at t is always 4 multiplied by t minus 1. So I know that if t is equal to 1, it's 4 minus 1, which is 3. Clear? Wonderful. Now let's see what else we have here. Now let's go and you practice the next question. Okay, guys? So let's begin simply. We have find equation of tangent line to curve f of x equal to, let's make it 5x squared minus 3x plus 10 at an arbitrary x equal to a. See if you can do that. Let's see if we can make it at arbitrary points. Thank you, Abhishek. Okay. Are we ready? So you see, guys, if you do it efficiently, it takes more less than a minute. So first we want to find the slope. So we have the function minus the function at a, so you take limit where x goes to a of 5x squared minus 3x plus 10 minus the same expression at a. Good? Divided by x minus a. Now I quickly group like with like. So 5x squared minus 5a squared, I can write it as 5x squared minus a squared minus 3x minus a. Do you see that? I group 3x and 3a. And finally, 10 minus 10 is gone. Good? Now what? Now I factor the numerator here, so that's limit as x goes to a of 5x plus a x minus a minus 3x minus a x minus a, limit as x goes to a. You see what I do, guys? I will factor out x minus a. So what will I get? I will get parentheses. What goes in outside of the parentheses is x minus a. Would anybody tell me what to write in those parentheses? Yes, what do I write in those parentheses, guys? I write 5 times x plus a minus 3. You all see that? How fast that goes. Divided by x minus a. Now I can cross the x minus a. And I can push the limit. Now there is no problem. You see why I crossed x minus a? Because x is not actually a. So I divide a number by itself, that's 1. Now, what do I get? X going to a, it's 5 times, so I get 5a plus a, x becomes a, minus 3, not plus 3, but minus 3. So what I see is that my slope is a plus a is 2a, so it's 10a minus 3. So to calculate the slope for this function, all I have to do is take the x coordinate at which, or the point at which I calculate slope, multiplied by 10 and subtract 3. Good? Everything else is obvious. You understand how to write the equation of the line, right? So simply take, this is the y coordinate, so it's y minus the y coordinate equals to the slope multiplied by x minus the x coordinate. So maybe I'll write it. So it's like this. So it's y minus, what was that? 5a squared minus 3a plus 10, I believe, right? Equal to the slope, which is 10a minus 3 multiplied by x minus a. That's the general equation of the line. And then simply substitute instead of a for the number at which you calculate the slope, and you are done. Easy, right? Not difficult. So we have what, 3 minutes before officially class is over. Do you want to begin a what when where question, or do you want another problem like this before? Or you don't want a what when question? That's also fine. We can just do more math. Another problem? Okay, another problem. So here is your next problem. Let's make it more interesting, yes? So I want you to tell me, here is y equal to 1 over x. Calculate slope at the point a 1 over a. Understood? What is y equals 1 over x? It means that to calculate the second coordinate, just take the first coordinate, take 1 and divide by the first coordinate. So I'm asking you, what is the slope? Okay, Abhishek, fine. You know, guys, actually, next time what we'll do is we'll make with I did it in the morning. We'll do pauses. I'll just do push-ups as you are solving it. Let's see how many push-ups. Will I get to 300 push-ups by the time you finish one problem? I already did 400 today, so I cannot go for it anymore. Maybe I should do sit-ups. Yeah, I'll do. Okay, you think about it, and I will try to use the time more efficiently for me. All right. Should we go over the problem? I'll wait, what, 1 more minute, okay, guys? 1 more minute, you try to do it, and if not, then not. Alrighty then, let's do it. So very simply, guys, look at it. It's algebra. Just take limit as x goes to a of 1 over x minus 1 over a divided by x minus a. Now, when you have two fractions, you want to come up with a common denominator. Yes? Limit as x goes to a is what? Common denominator, this has an a minus x over ax. And if I divide by x minus a, I multiply by x minus a here, right? Now look what happens, guys. Do you see what's the ratio between this and that? Yes? What's the ratio between this and that? If I cross it out, I'm left with minus 1. Do you see that? This is the same as x minus a multiplied by minus 1. They kind of cross out, but not exactly. They are minus 1. Good? And so now there is no problem. Okay, Moshe, take care. So now you can take limit as x goes to a. And what do you have? You have minus 1 over a times a, or a squared, which means all you have to do is take minus 1 and divide by a squared, and you are done with this problem. Good? Let me stop the recording.